Hello, reading quiz number 23. We continue our quest for relevance in calculus, and we look at the broad category called kinematics, and we'll study objects in motion, velocity, acceleration, speed, all those terms that you've known and loved for many years. So, the study of calculus originated from the study of objects in motion, which means Galileo's falling bodies, experiment to the study of planetary orbits. So this study, which we'll call kinematics, has driven many advances in the field and is the focus of the next couple of lessons. For a while, we're going to kind of use an idealized world to represent our objects in motion. They're going to move in just either one direction along a coordinate plane. As you know, life isn't like that, and we'll be talking later on about moving in multiple dimensions, 2 dimensions to start with parametrics, and then when you move on to calculus 3 or multivariable calculus, you'll start talking about 3 dimensions. So let's define some terms first. First of all, we have the position function. Sometimes you'll see this symbolized as s of t. If a particle is moving only along an x-axis, you'll see it as x of t or y of t, depending on the situation. Y of t meaning that you're moving on the y-axis. This function will describe the location of a particle or an object at a certain point. Then we can bring in what's called the velocity function, and velocity is defined to be the change in position over time. Hey, change in something over time, what do we know that is? We know that it is our derivative. So the velocity is the derivative or the slope of a position function. Formally, v of t is equal to s prime of t or ds dt if position is denoted by s of t. Units of velocity are often measured in units of position over units of time, such as miles per hour or feet per second. And then a particle is said to be stopped if velocity is equal to 0 at a particular instant. By definition, we'll say that if v of t is bigger than 0, the particle is moving right or up, depending on whether the particle is on the x-axis or the y-axis respectively. And then if v of t is less than 0, the particle moves left or down. Another function we'll consider more in the next reading, but introduce it here, is the idea of speed. In normal parlance, like speed is equivalent to velocity, but it really isn't here. It's calculus, it's defined as something different. It's particularly is the absolute value of velocity. It is thus always positive. So velocity you want to think of as speed with direction. So maybe you're moving left or moving right or moving in a particular direction. That would be velocity. And the speed is basically the magnitude of however your velocity vector is moving. So some other terms. We're going to use the term displacement to describe the net change in position from starting point to ending point. And then that's going to be distinguished from the term distance, which will be used to describe the total amount traveled regardless of whether you go forwards or backwards. So I have a runner in the diagram below. The runner moves to the right 50 feet, backwards 20 feet, and then to the right 70 feet. Forward 50 meters, dropped a stopwatch, runs backward 20 meters to get it, then runs forward another 70 meters. So the displacement will be the net movement. So notice that we go forward 50 meters, that's positive, negative 20 meters because we moved left, positive 70 meters, we moved right, and that's a total of 100 meters. Distance traveled, on the other hand, takes into account which, or does not take into account which direction we move in. Everything's going to be positive. So 50 meters forward. The 20 meters that we move backward is going to end up being positive. We put the absolute value around it. And then 70 meters forward gives us a distance traveled of 140 meters. So notice that's different from displacement. And the difference is 40 meters. Well, why is that 40 meters? Because we move backward 20. That backward 20 is going to be counted as negative with displacement and positive with distance. So the net is a change of 40. Distance traveled is going to be measured as the amount that you travel between each stopping point. Okay, the reason for that being at each stopping point, presumably you have a chance to change direction. So at each of those points, we need to make sure that we account for our change in direction. So let's use an actual function. A fish, for some strange reason, is moving along the x-axis. so its position at any time t bigger than or equal to 0 is given by s of t equals 4/3 t cubed minus 13t squared plus 22t minus 5, where s is measured in meters and t is measured in seconds. So first things first, let's find the velocity. Velocity is the derivative of position, or 4t squared minus 26t plus 22. When is the particle at rest? Well, particles at rest, as we defined, to be when velocity is equal to 0. You don't necessarily have to change your direction, but if that velocity is equal to 0, that particle is paused for that one moment. If we factor the velocity function that we got up here, we get 2 times 2t minus 11 times t minus 1, which gives us 2 stopping points at time equal to 1 and time equal to 5.5. When does the particle move forward and backwards? Well, we bring out an old friend. That's the sign test we learned about when we were doing our stuff with the increasing and decreasing functions. All right. After all, what does it mean to test when a particle moves forward? Velocity is bigger than 0. Velocity is the derivative of position. So we're doing a sign test on the first derivative. When does the particle move backwards? Velocity is less than 0. So we can do a sign test going back to our original statement. We notice that we've got a quadratic as our velocity. The quadratic has 2 roots. Both of them have a multiplicity of 1. And this quadratic opens up. All right, so our 2 endpoints will both have a positive value when we do our sign test on velocity. So positive at each of the ends. The signs will change in between because our multiplicities are 1. Now, we can go through and we can do a formal test, but that's just how it goes here. So the particle is going to move forward from 0 to 1 and from 5.5 to 10, if we consider 10 as our endpoint here. That's because velocity is positive, and backwards from 1 to 5.5 because velocity is negative. What is the displacement of the particle from time 0 to time 10? And what about the distance traveled by the particle? And describe the motion of the particle using a schematic diagram. Well, displacement is just change in position from starting time to ending time. S of 10 minus S of 0. If you remember, our position function was 4/3 t cubed minus 13t squared plus 22t minus 5. So we plug in 10 and 0 into that function. And we get 253.333. Distance is going to be found by finding the displacement from stopping point to stopping point and making each of those displacements positive. So our stopping points, remember, are 1 and 5.5. And then we take into account our endpoints, 0 and 10. So we need to find the displacement from S sub 1 to S sub 0. And from S sub 5.5 to S sub 1. So we notice we're splitting it up based on our stopping points. And from S sub 10 to S of 5.5. This is just a matter of plugging in numbers from our original equation, 4/3 t cubed minus 13t squared plus 22t minus 5. This is a good opportunity for you to use your tables. When you do that, you get 374.833. Now, let's make some connections between function and derivative graphs and position and velocity graphs. As I mentioned before, velocity is the derivative of position. So all the principles that we had looking at derivative graphs will apply if we're looking at velocity graphs. So let's say we have a graph of S sub t on the left and V sub t on the right. We know from advanced knowledge that S sub t is equal to t cubed minus 6t squared plus 9t plus 2. If that's true, then we can find the equation for the velocity of the particle by taking the derivative. We get 3t squared minus 12t plus 9. For what values of t is the particle at rest? Use the velocity graph to justify our answer. The particle will be at rest whenever velocity is equal to 0, which occurs at time equal to 1 and time equal to 3. And we can see those 2 times on our velocity graph. Time 1 is right there, and time 3 is right there. In both of those circumstances, velocity is equal to 0. For what values of t does the particle move backwards or forwards? Use the velocity graph to justify your answer. The particle is moving forwards when velocity is bigger than 0, which is from negative infinity to 1, and from 3 to infinity. The particle moves backwards when velocity is less than 0, which occurs from 1 to 3. And then at what time is the particle moving backwards the fastest? That is asking us when is our largest speed value. If we take a look at this graph on the interval, our largest speed value will either be our largest negative velocity or our largest positive velocity. And it appears that our largest velocity is going to occur positively at 0 or at 4, and our largest velocity negative will be at 2. Well, how can we actually figure that out? The particle moves backwards the fastest at the lowest point on the velocity graph, which is specifically what it's asking. This occurs at time equal to 2. That happens to be an inflection point for the graph of S sub t. I wonder why that is. Oh wait, connections between the first derivative graph, relative maximums on that graph, and inflection points, and that's the connection here. Alright, now we bring in our good friend Aladdin. He flies on the magic carpet with position in miles shown at time t minutes, where s is a differentiable function of t. The selected values for the position are shown in the table below from 0 to 90. So, this is a chance for us to bring in all kinds of different aspects of our calculus experience. First question asks why s of t is equal to 20 between 10 and 20 minutes. Well, one thing that we can look at is s is differentiable, that's given, so s is continuous. If we want to find where s of t is equal to 20, then that's where we bring about our good friend the IVT. S of 10 is equal to 17.1, S of 20 is 24.7, so 20 is in between those two outputs, and therefore we know that there's some input in between 10 and 20, so that S of c is equal to 20. Second part, approximate Aladdin's velocity at time t equal to 35 minutes. Show the work that leads to your conclusion. Well, again, we're approximating, so we need to figure out what intervals might be helpful here, and it looks like the interval from 30 to 40 will be the most helpful. Remember, we approximated our derivative using our average rates of change, and that's what we can do here. Notice I use an approximation sign. V of 35 is approximately V of 40 minus V of 30, divided by 40 minus 30. Plug in our values, and we get 1.04 miles per minute. Remember, when using the table, make sure that you cite the values in the specific function that we're using from the table. Is Aladdin stopped for any time in between 0 and 90 minutes? Explain your reasoning. How will we figure something like that out? Well, and later on we'll study in a little more depth this thing called Rolle's theorem. So let's talk about this a little bit. Basically, if we know that a function's differentiable and therefore continuous, we know that if two values are the same at two different points, then we know the derivative has to be equal to 0 somewhere in between. The function has to turn back around to reach the point that's the same y value. So in this case, if you take a look, we notice that in between 70 and 80, we know that the position has to be equal to 81.3. That's our IVT. All right. Now, why in the world would I choose 81.3? Well, if we know the function has to be equal to 81.3 somewhere between 70 and 80, and the position is equal to 81.3 at 90, since those two outputs are the same, we know the function has to turn around at some point in between. And if the function is turning around and is differentiable, then we know that the derivative is equal to 0 at some point. So, if the derivative of position is equal to 0, we know velocity is equal to 0.